some graphical summaries of quantitative data, we're going to move on to numerical summaries of quantitative data. And our graphical summaries are going to help inform which numerical summaries are most appropriate. Let's start off with this key feature, this idea of measuring center. Now, I expect you've seen these measures of center, mean and median, before, but hopefully you can see them in a new light. So mean, we're going to think of as the balance point in the data. Median, we're going to think of as the middle observation of the ordered data. So let's remind ourselves, if we're calculating the mean or average of a data set, what symbol or notation should we use? Right, we're going to use X bar for that. And if I asked you, how do you find the mean of a data set? Most of you would probably say something like, add up all the values. So if you haven't seen it before, depending on your math background, that capital Greek sigma there means sum. So sum up all the x's, or all the data points, and divide by n, how many you have. So here's a new notation we're going to be using. Little n, if you write in capital letters, don't do it right now. We're going to reserve big N for something else. So little n just means number of observations in our data set. So add them up, divide by how many you have. The median, our middle point, is the median. And if you have an odd number of observations, the median will be one of those data points. So n odd, median is a data point. If you have an even number of observations, so n, the number of observations, is even, the median is going to be the average of the middle two. Median is average of the middle two observations. Excuse me, you'll notice I'll be using this for abbreviating observations throughout the notes here. So let's do a couple of examples to help us really appreciate and understand the difference between mean and median, and point out when we should use each of these. So bear with me, I know this is really corny, but go with it. So in this example, we've got a seesaw, and we've got kids, it's marked off every foot, and we've got kids sitting at 3 feet, 4 feet, 5 feet, 6 feet, and 7 feet. And I'm going to draw these kids as blobs here that are all magically weighing the same amount. If you're more artistic and want to draw some actual stick figure type kids here, go for it. But I've got these 5 kids, all magically weigh exactly the same amount, sitting on my seesaw. So let's think first about the mean of the data. Just eyeballing it, if I want to talk about the mean, we said it was the balance point. So where would you put the fulcrum here to balance this seesaw out? Hopefully it's pretty clear. We'd put it here at 5 feet to balance this. So the mean is 5 feet. I found that out without doing any math, but thinking of it as the literal physical balance point. I could do the math and add up the data points, 3, 4, 5, 6, and 7, then divide by how many we have, 5 kids, and we would get that mean of 5 feet. Now let's talk about the median, the middle data point. That also will be 5, not a big data set, kind of easy to just look at it and see. The middle of that ordered data set is 5. So in this particular scenario, mean and median are the same. If everybody shifted up 2 feet, how would mean and median change? Hopefully it's obvious, those would also shift up 2 feet. Now let's change up our example a little bit. Suppose that this guy, little John here, sitting at 7 feet, for whatever reason, he's rather shy and decides to move way up to 17 feet. So let me draw my new picture here. Maybe not to scale as much, but we'll kind of eyeball it. 3, 4, 5, 6, 7. I've got these kids at 3, 4, 5, 6. This one at 7. Instead of sitting at 7 feet, I'm going to move his dot way down here to 17 feet. So he's moved down to the end of this seesaw that also magically can grow depending on how many kids are there and where they want to sit. So they all weigh the same. This guy just moved down to the end. So the question is, thinking about the mean, what's going to happen to that mean in this scenario compared to the previous? The mean, we said, is the balance point in the data. So when this guy moves over here, we expect the mean to shift to the right to balance out that observation, or in other words, the mean will increase. And the median should stay exactly the same. I still have 2 data points below 5, 2 data points above 5. So let's write that down. Our mean, add up our data points, 3, 4, 5, 6. Instead of 7, he's moved down to 17. Divide that by 5. If you work that out, you get 7 feet. The mean has indeed shifted from 5 feet over to 7 to balance out little John who scooted down. And then let's just record it here. We already talked about it. The median is 5 feet still. At 5 feet, I still have 2 points below, 2 points above. It's still in the middle. So let's kind of put some of these things together. Our next vocab word here is this idea of a statistic or a calculation being resistant if it's influenced very little by extreme observations. So which measure of center is resistant? Our options, we've got mean and median. And again, being resistant means it's not really influenced by changing of observations. Let's think even more before we answer. If I changed little John's position to 17 million feet, what's going to happen to the mean? It's going to have to shift way over here to balance little John out at 17 million. What about the median? The median's still going to be 5. I still have 2 points below 5. I still have 2 points above 5. One of them's just really, really, really far above it. So mean is changing as those extreme observations change. So the mean is definitely not resistant to changes in the extreme observations. The median, though, is resistant. I can change how far out little John is. Doesn't matter. The median is still going to be 5. So what does this mean for us when we're deciding which measure of center to use? Let's take a look and kind of summarize what we observed in some plots. So first, suppose our data looked something like this. What shape does this data have? Yeah, it looks pretty symmetric. The left and the right match up. And if I want to talk about measures of center, the balance point or the mean would be right here, and the median would be basically right here as well. So that's like our first case where our kids were sitting at 3, 4, 5, 6, and 7 feet. Pretty symmetric and evenly spaced. Mean and median should be about the same. I should note that in real life, this equal to is going to be approximately. Mean and median rarely are exactly the same thing in real life, but they should be about the same. Next, what if we had some data shaped like this? Maybe the mean or the the median, the half and half is somewhere down here. We have a lot of data here and here. Where would the mean or the balance point be for this one? Think carefully, and maybe remember the previous example with little John to help you out. If you're thinking that the mean is shifted right, you're correct. Think about little John, that outlier, that skewness, that pull. The mean was pulled in that direction to balance or account for that. So here, the mean would be shifted or pulled towards the right. I should note these are not drawn to scale, so that may be a bit misleading. And then let's draw one more here. This one is our left skewed, it's pulled to the left. So if my median is here, my mean is going to be pulled to the left to balance out that skew. So let me label these also just for review. Here's our symmetric. Here's our right skew because the tail is pulling towards the right. And this one is our left skew because the tail is being pulled towards the left. And we saw this general pattern here. The mean is pulled in the direction of the skew. Mean pulled towards the skew. Make sure you know this. Put a big star in this whole section, this big gray box up here. So to kind of sum it up, if the data is skewed or has outliers, we should definitely use the median over the mean. And the reason for this, think back on little Johnny on the previous example, as we moved him further and further out, the mean is going to get pulled further and further out and not represent the bulk of the data. We want a measure of center that represents the bulk of the data. So when you have skewed data or outliers, use the median because it will not be influenced by the skewness or the outliers. If the data is symmetric, we're going to use the mean. It might seem strange. You might say, well, can't I just use either one? Because they're going to be basically the same. But the mean has a lot of nice properties, so we'll use the mean when the data is symmetric.